Welcome everybody. This is our first session in NEET previous year questions for chapter Alternating Current of class 12th. Before this video, in this series we have made previous year question videos for around 6 chapter of class 12th and all the chapters of class 11th, and all of those videos are available on our channel's playlist section. We have also started similar series for JEE previous year questions. So if you are preparing for JEE or some of friends are preparing for JEE, or if you want some additional practice, you can also watch those videos. And if you find these videos helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video with question number 1. And let me adjust pen thickness. So peak voltage of AC source is equal to, we have been given here the value of voltage supplied RMS root 2 times of the RMS value 1 by root 2 times of the RMS value. So if we draw a curve for AC, then our AC current will look something like this. And this value is known as RMS value, and this value is known as peak value. And there is a relation between RMS and peak, that peak value is root 2 times of the RMS, or we can say RMS is equal to 1 by root 2 times of the peak, and that is almost equal to 70.7% of the peak value. So here option D, that root 2 times of the RMS value of the source is the peak value, that will be the right answer. Let's move to the next one. In the inductor shown below, inductance L is connected to a AC source. The current flowing in the circuit is I node sine omega t. The voltage drop across the L is. So we have to find out voltage drop across the inductor. So voltage drop across the inductor will be given by VL is equal to L di by dt. Now there is a small caveat here, that if we find out that induced EMF across induced EMF across inductor is given by minus L di by dt, and voltage drop will be positive of that, because that is the amount of voltage. Suppose due to the AC source we supply 10 volt here to the terminals of this we can say inductor, and due to induced voltage it produces minus 3 volt. So final potential across it, that will be, we can say, a final drop of potential that will be of 3 volts, because this minus 3 volt will be added here. So drop of potential across this potential this inductor will be of 3. So we will take VIL is equal to L di by dt. So we know the expression for I, so it will be I node derivative of sine omega t, that will be cos omega t into omega t's derivative, that is omega. So L I node omega cos of omega t. So L I, here it is, omega L into I node into cos of omega t. That is option D for us. Let's move to the next one. A light bulb and an inductor coil are connected to a AC source through a key shown in the figure below. The key is closed, and after some time iron rod is inserted into interior of the inductor. The glow of the light bulb So we have to find out glow of the light bulb. Now consider the scenario before inserting the rod. So we can say case 1, without rod, without iron rod. So in this scenario, what will happen? As we have an inductor here and we have a voltage supply here. So, and this is a AC source that you need to remember. This is a AC source. So inductor, due to this AC source, inductor will charging, and there after inductors gets fully charged, then there is a shift in cycle. So inductor keeps on charging and discharging. As this is AC current, means there are cycles of positive and negative potential and positive and negative current. So due to that, inductor will keep on charging and discharging. But then we can find out the glow of the light bulb, as glow of the light bulb depend upon the amount of current flowing through the circuit in the stationary states. We here we assume that inductor charges very fast, so there is certain time that for which there is a constant current flowing in the circuit, and value of that current will be given by I is given by a V divided by the impedance of the circuit. Oh, sorry, we can say Z, impedance of the circuit, and that will be given by V divided by resistance of this bulb, that is Rp square plus XL square, where the XL is the impedance offered by the inductor, and we know value of impedance, that is Rb square plus XL is equal to omega L, so it will be omega square L square. So if we change here any of these values, so current in the circuit will change, and if current in the circuit changes, then we can say intensity of the bulb will change, because intensity is just the power consumed by the bulb, and power consumed by the bulb will be I square into resistance of the bulb, where I is the current which is governed by this equation. Now case 2, when we insert iron rod. So when we insert iron rod, we know that this is a coil, and mutual inductance of a coil is given by mu node n square into area into its length, where n is the number of turns. So here neither n is changed, neither L is changed, neither L is changed, but mu changes because we insert a iron rod, so it becomes mu r mu node n square a L, means L increases, self inductance of the coil increases. Now if L increases, we can say this total impedance Z increases, and due to current will decrease in the circuit. And if current decreases in the circuit, means power consumption across this bulb will decrease, and so its intensity will decrease. And we can also solve it in a different way. We know that potential drop across a inductor is given by L di by dt. So if L increases, potential drop across this inductor will increase. Suppose our total supply was 220 volts, and out of this 220, initially a drop of 100 was across the inductor, and remaining 120 was across the bulb. Now due to increase of L, this 100 becomes 120, suppose. So now this bulb only has 100 volts, and in this scenario we can use that power is consumed is V square by R. So potential across bulb decreases, so its power will also decrease. So we can say eventually glow of the bulb will decrease. Now let's move to the next one. A coil of self-inductance L is connected in series with a bulb B and AC source. Brightness of the bulb decreases. So we have to explain that when brightness will decrease, when frequency of the AC is decreased, number of turns in the coil is reduced, capacitance XC is equal to XC included in the same circuit, and iron rod inserted into the coil. So let us examine all the options one by one. Now we know that suppose if we have a uh, circuit in which there is inductor and there is a bulb, so bulb will act as a resistance. So current in the circuit, which we already solved in our previous question, that current in the circuit will be given by supply by impedance, total impedance, and that will be R square, that is the resistance of the bulb, omega square L square. This is the resistance offered by the this inductor. Now, if frequency is decreased, frequency of AC is decreased. If frequency is decreased means omega will reduce. And if omega will reduce, then this whole term, this impedance Z terms, if omega goes down means XL goes down. The impedance term or impedance of the cell inductor goes down. Due to that, Z goes down, and if Z goes down, then current goes up. And if current goes up, power across the bulb also goes up. So option A will not work. Now number of the coils, number of turns in coil are reduced. We know that self inductance of a coil is again mu node n square A L. So if n is reduced, L is reduced, and again if L is reduced here, again XL will be reduced, Z will be reduced, I will increase, and power will increase. Now in the third option, so B is also cancelled out. In the third option, XL is equal to XC, a capacitor included. Now we know that actual formula for Z is, it is R square plus XC minus XL square. So if they are offering equal impedance, so this will impedance of both of these will cancel out, and we can say Z will decrease. And if Z will decrease, again this cycle will start and power will increase. So we have only option D is left, and that we already solved in our previous question, that when we insert the when we insert a rod of inside a coil, and that is made of iron, then its inductance increases, self inductance increases, and due to that resistance, impedance offered by it increases, and that causes decrease in current, so intensity will drop. Let's move to the next one. So in steady state, uh, current in the circuit. So we have to find out current in circuit in steady state. Now in steady state means after some long time, and after some long time we know that this capacitor will not conduct DC current. Capacitor only conduct DC for very small time, and that is until it is charging. After it's charging, it does not conduct DC current. So uh, in steady state it will not be functioning in the circuit, and if capacitor is not functioning in the circuit, then this 5 ohm resistance is also broken from the circuit. It will be look like this. We have 10 ohm here, sorry, 2 ohm. This is 10-volt battery. Capacitor is broken from the circuit, and we have 5 ohm here, and we have a 3 ohm here. So as one of the terminal of this 5 ohm resistance is not connected, means this is also not taking active part in the circuit. So we can exclude this 5 ohm resistance, and our circuit, final circuit, will be something like this. We have a 2 ohm here, we have a 3 ohm here, and we have 10-volt battery here. So current will be total potential by total current, 3 plus 2 5, that is 2 ampere. This is the amount of current in the circuit. So option C will be the right answer. Let's move to the next one. A 10 microfarad capacitor is connected to 210 volt 50 hertz source as shown in the figure. The peak current in the circuit is nearly. So we have to find out value of the peak current and assume, let us assume that this is the value, this is the peak value, I think. Oh, no, sorry, not peak value. Normally when it is written in this form, then it is a RMS value. So we have been given VRMS. VRMS is 220 volt. As we have to find out peak value of current, so I peak will be V peak divided by the impedance of the circuit. So V peak will be here root 2 times of the RMS value and Z we will calculate. Now as this is a capacitor, so for capacitor XC, that is impedance offered by the capacitor, is 1 by omega C. So omega is here 52 pi into 50 into capacitance is 10 microfarad, so 10 into 10 raised to power minus 6. So it will be 1 by pi 50 into 200,000. So this will be 10 raised to power minus 3 or 10 raised to power 3 by pi. This is the value of the impedance offered by the capacitor. And that will be equal to Z because we don't have any other component here. So I will be I peak root 2 into 210 divided by Z, that is 10 raised to power 3 into pi here. So this will be root 2 into 21 into pi divided by 100. On solving all this, we will get 0.9297 and that closely matches with option A. Now let's move to the next one. AC source is connected to a capacitor due to decrease in operating frequency. So if operating frequency decreases, it means omega will decrease. Omega is the angular frequency, that is 2 pi times the frequency, so it will decrease. And we know that XC or impedance offered by a capacitor is 1 by omega C. Now if omega decreases, it means XC will increase, and if XC increases, we can say current in the circuit, assuming this is only purely a capacitive circuit, and even if we have some resistance, then impedance is given by R square plus XC square. So if XC increases, Z will increase, so current in the circuit will decrease. So now let's examine the options. In the option B, capacitive reactives remain constant, so that is wrong as it is increasing. C, capacitive reactance decreases, so that is also wrong as Xc is increasing. Now displacement current increases and displacement current decreases. These are the two options that we have to find out. Now in case of capacitor, if we have a circuit where we have some capacitor, then outside of the capacitor, the current flowing in the circuit is normal current, and inside of the capacitor is the displacement current. And we know that normal current and displacement current are equal in magnitude. So if normal current decreases, then it means displacement current will also decrease. So option A is the right answer here. Now let's move to the next one. A 40 microfarad capacitor is connected to supply frequency. RMS value of the current in the circuit is. So we have to find out RMS value. For that, what we need, we have the RMS value of the, we can say, voltage here. We need value of the impedance. So impedance offered by capacitor is 1 by omega C. It will be 2 pi into frequency, that is 50. Capacitance, that is 40 microfarad, so minus 6. So this will be 100 into 1000. So 1 by 4 pi into 10 raised to power minus 3, or 1000 by 4 pi, or we can say 250 by pi. That is the impedance. So current RMS value will be Vrms by Z, and as this we have only capacitor in the circuit, so Z will be equal to XC. So it will be 220 by 250 into pi, and solving this, one thing, potential is 200, so it will be 200 to 20 pi by 25, and solving this we will get 2.51. That is option B for us. Now let's move to the next one. A 100 ohm resistance and a capacitor of 100 ohm reactance are connected in series across a 220 volt source. When the capacitor is 50% charged, the peak value of the displacement current. So we have to find out peak value of the displacement current, and capacitor is 50% charge here. So from that we can get the value of time. So let's start. As we have to find the current, so first let's find the impedance. So Z will be R square plus XC square, that will be 100 square plus 100 square, that will be 100 root 2. So this is the value of the impedance, and from this we can find out the current flowing in the circuit. So current flowing in the circuit, I will be V by Z. So V will be, as mentioned, is 220 divided by Z, that is 100 root 2. So that will be 2.2 divided by 2. And we have to find the peak value. So peak value of this current, and this is the calculation here I am doing are for the normal current, not for the displacement current. These are the normal calculation for the normal current. So I peak for the normal current will be root 2 times the root 2. So it will be 2.2 ampere. Now we know that our normal current is equal to the peak current, is equal to the displacement current, just they are at different location. If I current is flowing in the wires, then I current will be flowing inside the capacitor in the form of displacement current. So this will be equal to the peak of displacement current, that is 2.2 ampere here. So option A will be the right answer. Now let's move to the next one. The reactance of the capacitor of capacitance C is X. If the both frequency and capacitance is doubled, the new reactance will be. So we know reactance is given by 1 by omega C, and omega we can write 1 by 2 pi F into frequency into C. Now if we double the frequency and double the capacitance, so it will be, suppose X dash 2 pi of 2F into 2C. So it will be 1 by 4 of 1 by 2 pi Fc, and it will be X by 4. So reactance will decrease to X by 4. That is option D for us. Let's move to the next one. The amplitude of the charge oscillating in a circuit decreases exponentially as this value, where q node is the charge at t0, the time at which charge amplitude decreases to zero point 0.5 node of nearly. So it is basically a discharging of a capacitor. This is the discharging equation of a something like equation for a capacitor, but it is not directly mentioned, so we will not include here any capacitor or thing. We will just follow this equation. Here we have inductor also, because L is also mentioned. So discharging equation is Q is equal to Q node e raised to power minus RT by 2L. and we have to find out time at which charge amplitude is zero point 0.5 of the q node. Zero point 0.5 of the q node means half of the q node, so q becomes q node by 2, q node e raised to power minus rt by 2l. Q node get cancelled, we have half is equal to minus rt by 2l. Taking antilog of both of sides, it will be minus ln2, because ln1 is 0, is equal to minus rt by 2l. Negative signs get cancelled, and we have time is equal to 2l into ln2 divided by the value of resistance. So twice L is 12 millihenry, 12 into 10 to the minus 3. ln2 is 0.693 as per already given here, and resistance is 1.5 ohm. So solving all of these, we will get 11.09 into 10 to the power minus 3. That will be 11.09 millisecond. So with this, I end this video here. Again, you may found this video helpful and useful. And if it is the case, then do press the like button, share it as much as possible, and subscribe to our channel. And if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.